Okay, let's complete the implementation of simple skigram. First one is forward method. We first need to convert target into a word embedding. That is done through in layer. We pass target here. In the previous case, we passed context here. And the next thing we need to do is pass this H to the output layer. Okay, and the first loss is going to be calculated through loss layer 1, and it has to be able to predict the first context on the left side, and also need to be able to predict the next context on the right side. Some of them might think this implementation is somewhat weird. However, it's not weird at all. Let's say this as predict scores for each word. Let's say we have only 10 words in our dictionary. Then it has like 10 scores. And with this just one vector, you can predict 2 outputs. Let's say it predicts this number like this. Then when we calculate softmax, it only cares about the score of the correct label. So when it calculates the loss for the first one, comparing with the left context, it cares about only this number. However, when it calculates the loss with the right context, then it only cares about this number. So this output actually contains 2 high numbers, one for the left context and the other for the right context. However, this skigram does not care about the order, whether it's on the left side or on the right side. It's perfectly okay. That's why we can use 2 loss layers for a single output. And with this single output, this skigram can predict the context. And the total loss is going to be L1 plus L2. And we're going to just return the total loss. And the backward pass, because the loss is the last layer, we need to calculate the gradient from this layer. And we do the same for TL2. Like this. And DS, this S gets divided into L1 and L2. So it should receive gradients from both L1 and L2. That's the principle. So DL1 plus DL2 is what DS. And we pass DS here. And pass DH here. Return none. Okay, up to this point, we have implemented simple CBOW and simple skigram. And how do we actually train this simple CBOW and simple skigram? Let's see the train code. The first thing we need to do is define some hyperparameters, like window size is set as 1, and hidden size, and batch size, like this. So we are, another thing is max epoch. How many epochs we are going to train. So these are some parameters, okay? And we need to have a text to train our skigram or CBOW. Just say goodbye. I say hello. And we are going to create corpus, word to ID, ID to word by using pre-processing. You can also load the PTB data, load data chain like this. Anything is okay, but we're just testing a simple CBOW and simple skigram. So we rather use simple text because it takes quite a lot of time to train simple CBOW and simple skigram. And the vocab size is going to be the length of word to ID. And we need to create contexts and target using create context and target function. We already implemented this function in the beginning of this session, window size. And we need to convert one hot and the context as well. And we create simple CBOW or skigram. And we define optimizer as Adam. And here is a new thing. Now, we are not going to define or write the code for training. But here we're going to use something called trainer. We just pass model and the optimizer, then it does the rest of the job. And nowadays, there is something called PyTorch Lightning, and TensorFlow also offers similar things, something like trainer. And nowadays, you don't have to write your train code on your own. You just define your model and then pass that model to trainer. And this optimizer gets a lot of parameters. However, this is very simple implementation, so we don't need to pass any parameters to Atom here. But you can do in PyTorch or TensorFlow. Anyway, the beauty of trainer is we don't have to write the training code for ourselves. It does the job for us. And as you can notice from our previous sessions, the training codes were quite repetitive. We are basically using the same concept again and again, like loading data, passing forward pass, calculate loss, and then backward, and pass those values to optimizer. That was basically what we do for training. And this trainer does the training job for any types of model or optimizer, okay? And what we need to do is just call the fit method. You pass the data and the target and the max epoch and the batch size, like this. And some trainers offer methods like plot or how it's going on, how it is well doing, things like that. Okay. And after the training is over, we can get our word vectors from models, word specs, and we can do some fun jobs like we can print word vectors, or we can plot word vectors on 2D plane, and we did that in the previous video. And you can play with word vectors like word analogy or other intrinsic and extrinsic jobs. All right, so we now understand by using trainer, we don't have to use all the same repetitive training code. Then how can he implement this trainer? This is more of machine learning or deep learning engineering. And when you apply for deep learning engineer to deep tech companies, then this is what you might do. Okay, implementing this kind of optimized code. Okay, let's implement trainer together, and this will be in the utility section. Okay, let's implement trainer first. Class trainer. First, we need to implement the initializer, model, and optimizer. Of course, the trainer offered by PyTorch or TensorFlow receives much more parameters, and you can set a lot of options. However, we are using just a simple implementation. We're passing just model and optimizer. The self-model is model. Self-optimizer is optimizer. 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 And we're going to keep track of the losses, and we're going to store the loss. And self-eval interval, none, self-current epoch, 0. Okay, the next method we need to implement is fit. It receives the data and target, and how many epochs it is going to train, and the batch size, max grad, and eval interval. All right, and I'm going to talk about what max grad is about soon, so don't worry about it. We first need to get the data size, how many data we have for training, to calculate the max iteration. We divide data size by the batch size, then we can get the number of iterations. And self-eval interval is eval interval model and optimizer, our self-model, self-optimizer. Total loss is 0. Loss count is 0. And start time is time. We are going to import time here. We want to log how much time we have spent on training. So we are keeping track of the start time. For epoch, we range max epoch. We first shuffle the data. Why do we need to do this? Because if the data are in a row in very organized way, then that order can bias the training process. Therefore, we need to mix or permutate the data order so that we can remove the bias. Okay. The user had to do this on their own. However, sometimes users might forget about that, and we can do that for users. And we shuffle the data like this. And the label like this. And for iterators, you range max iterators. We get batch first. Iter's times batch size, iter's plus 1 times batch size. We saw this code in the previous slides, previous sessions, and we get the batch of labels. Okay. What we are going to do is first pass the data to the model, batch X and batch T, and get the loss. And we do backward first, and they get parameters and grades. And we're going to do something called remove duplicate. I'm going to talk about what this is about shortly. Anyway, we need to remove duplicate. And if there is max grad option, then we're going to clip grades. I'm going to also talk about what clip grades is. So the job is we need to implement remove duplicates, and we also need to implement clip grades. Okay. Anyway, we need to do these jobs. And after that, we could finally pass our parameters and grades. And we can add up the total loss and loss count plus 1. This is basically what we did for training. And we write this code again and again. And this trainer class automates that job, that repetitive job. Okay. And from time to time, we might want to display the training process to the users. And that is sometimes called evaluation. If eval interval is not known, user wants us to display the training process, and iter's eval interval equals 0, then it's time to display the training process. We calculate the average loss, total loss divided by loss count, and elapsed time is time minus start time. And we just print epoch, iter, in time, in second, and loss. Because we count from 0, we add 1 here. Iter's plus 1, max iter's, elapsed time, and average loss, like this. And self-loss list, we append the average loss. And we reset the total loss and loss count as 0 and 0. And we add current epoch, increment current epoch. Okay. And we can also implement some utility methods for trainer, like plot. And this one plots nice graphs of losses. That's why we're keeping all the losses in our loss list. That's why linear. And we can plot X loss list, label as train, X label. So this is basically up to you. You don't have to follow this implementation. And if you want to visualize other things, you can store those values as class attributes and then plot here. Okay. ELT show. All right. That's how we implement this trainer. Now we also need to talk about what remove duplicate and what click grids are about. Okay, let's first talk about remove duplicates. As we saw in this simple cbow, this metmul shares the same win. We use the same win twice. That means these parameters are duplicate, and we want to remove that because that could somehow spoil the training process when we pass those parameters to optimizer. And that's the job of remove duplicate. And how can you implement this remove duplicate? It's going to receive params and grades like this. And we are going to first copy params and grades like this. While true, find flag false, and fill parameters. We need to find the shared parameters. If the parameters I is parameters j, that means they are shared. This is operation compares whether two objects are the same objects or not. And if that is the case, we collect all the grids in one place, like this. And we turn find flag as true. And from parameters, we pop j. And from grids, we pop j also. And sometimes, if the parameters are just the same, but one of them might be transposed, and we want to find the case as well. So if the transposed one is the same as the prime j, and if that is the case, we're going to basically do the same thing, like this. However, we need to do transpose here, okay? And other things are just the same. And if find flag is on, then we need to break, because we don't have to search any longer for I. And if that is the case for the next case, we also break. And after all the iteration, if the find flag is still not true, then we just need to escape from this while loop. And after we process all the parameters, we return params and grades. All right, what's about click grades? Grades receives max norm, meaning gradients cannot be bigger than max norm. And if sometimes that happens, gradients can explode. When we multiply multiple large values, then they can go wrong. And we saw one picture in the optimization class that if gradients are too big, then even though the current state is near to the optimal point, it could go wrong, like go to somewhere absurd when the gradients are quite big. And to avoid that situation, we sometimes want to seal the size of the gradients. That's done through click gradients. You first calculate total norm. So calculating total norm is just simple, like this. And we calculate the rate between max norm and total norm. And if rate is smaller than 1, that means some of the gradients already exceeded the max norm. Then what we are going to do is multiply the rate, the gradient. So as you can see here, there are many jobs we need to do, like click gradients and remove duplicates. And you might have realized that when you implement some trainers or other things, you need to check many side cases. And here we haven't cared about all those side cases because sometimes data size and the X and T might have different sizes. We need to check those cases. So when you do machine learning engineering, you need to care about all those error cases. Okay, that was about implementing naive, simple CBOW, and simple skigram. You can run this code block and train your word vector and play it on your own. And in the next video, we're going to implement improved version of CBOW and skigram.